An actuator is a transducer converting to mechanical energy. So I could have some form of energy, electrical energy being very common, and I want to convert that to some mechanical energy, some motion or some force output. That would define an actuator. Remember, the transducer part of it is just some energy conversion. A sensor is also a transducer. I can think of an actuator kind of as the reverse of a sensor. In the actuator's case, I'm acting upon an environment that's providing a load on my actuator. And the actuator is a direct interface to that environment. And in order to drive that actuator, I'll ultimately need some power amplification and modulation. So I can think of those effectively as my interface electronics that I had between the sensor and what would effectively be back here as my microcontroller or some other kind of low power electronic interface that I want to be using to control the actuator. So my actuator at this point is providing some kind of physical signal, and that might be something like a torque, or it might be a displacement or a rotation, right? I can come up with a lot of different physical signals that I might have here. In this case, typically this signal right here will be something like a voltage, but in something, for example, like a hydraulic actuator, this might be some kind of fluid flow or pressure. Same for a pneumatic actuator. For piezoelectric actuators, it'd also be something like a voltage or a current or a charge, right? But some kind of energy right there. And then usually at this point, this is also kind of a voltage output from a microcontroller, either a microcontroller or a DAC. I might also have controlling this as well, but usually a voltage output there. And an interesting distinction that I have in the actuator side of things, and I can kind of think of something similar in sensors as well, it's basically on this side I'm looking at kind of a low power interface. So these might be kind of 5-volt signals, fairly low current. Over here, I'm looking at fairly high power output. And so this might be, amps of current versus the, 10 milliamps that you could get coming out of an Arduino, for example. And this block right here that we'll talk a little bit more about in a bit will be the power amplification and modulation to go from this low power side to the high power side. As a quick example of that pathway, let's look at an electrical actuator. Most of the electrical actuators that you'll encounter are going to be electromagnetic in some fashion, and the best example of that we'll dive deep into is a DC motor. But I'm just going to give you the preview of what we're going to be talking about right now. So this would be kind of an example DC motor. It has some output shaft that would be rotating around. I could have some load applied to that. That would be some load torque, basically. So it'd be trying to rotate something, for example, and that would provide the load torque as well. But this would also have some speed associated with it, omega as well. So those are kind of the two outputs of my motor, the torque and the speed. Now, as we'll talk about, I can actually represent this motor by this fairly simple model here of a resistor, an inductor, and a voltage supply all in series. So this equals this model here. And of course, to that motor, I want to hook up my interface electronics, or kind of my power amplification and modulation stage. And the way that I'm going to do that in general is through transistors. And transistors are going to give me the opportunity to provide a separate power supply. So now I have a separate supply coming in here that I'm calling V motor. And this output would ultimately be linked here to drive my motor here. And then this side of this circuit would be kind of the control signals that I might have coming from something like the Arduino outputs. So that could be driven by one of the digital outputs on your Arduino, could be providing that control right there. So this is a very simple example of how I go from my actuator stage and some motion and load applied on the environment the power amplification and modulation, and the Arduino that is talking to that particular stage as well. And so once again, we have kind of the low power side of things, which is this orange path here, and then the higher power side of things, that is the red path. Right? That is providing some other supply, typically, is what you would have in an actuation setup, that you can provide the kind of high powers that you need to drive these things. Another example to consider might be a pneumatic cylinder, and I can think of this in terms of pneumatics or hydraulics as well. And in this case, I just have a piston, and I have some kind of valve that I can apply pressure to, or some flow to fill this chamber and move this thing. So out of this, I'm going to get some force and displacement at the end of my piston here. In this case, maybe I've set this up with some kind of spring associated on here so that it can return and I don't need to push air in on the other side. In this case, my power amplification and modulation stage would actually consist probably of that valve right there. So this stage would effectively be driving this valve. So let me define that. That's my valve right here. And by controlling that valve, along with some other reservoir of pressure, so I might have some kind of compressor up here that I can send air into that valve with. So this is kind of my power supply equivalent in my pneumatic system. Right? By controlling that valve, I can control the flow of air into this cylinder here. And then, of course, the idea is that ultimately something like your Arduino or some other microcontroller could actually be used to switch these valves. So maybe there's some kind of solenoid, which are electromagnetic actuators on their own right, and I can actually drive those with an Arduino. There are obviously a number of metrics that I'm interested in when I'm actually looking at or trying to decide, for example, on a particular actuation method to use in my mechatronic system. One of the most obvious ones would be the kind of torque or force output that I would get from that system. Another way to think about that would be what loads I could actually apply on my environment. Second metric would be how fast I can actually move. So I'm trying to kind of exert some physical displacement. How fast can I do that? How fast could I change that force? I can also think of this effectively as bandwidth. Output power is obviously a combination of the speed and torque outputs. And another kind of common metric might be specific power, where I'm looking at output power per mass of the actuator. So if I want a lot of power in a small package, this would be the kind of metric that I'm interested in looking at. Efficiency, of course, is often very common. In this case, I'm looking at output power, which is often my mechanical output power. So that would be my force times my speed, for example, divided by the input power that I put into the system. So that might be something like the electrical power that I use to drive the actuator. And then depending on application, obviously you have a whole host of other metrics that you might be interested in, kind of minimum step size that I could have my actuator take, the positional accuracy, if I'm really interested in controlling a specific position that I might be interested in for a 3D printer or something, for example, that position accuracy would be very important for me. So there are a lot of other things that I could consider depending on my application in terms of metrics for actuators.